Let's talk data. How do we read tables? How do we interpret them? And what can we do with that? So very simply put, we need to be able to read data that is put into a table. So a table might just break down data for us into different categories, how many things, people, items in different classes. By and large, you will always have two axes, and we are looking up basically where lines and columns intersect. So the pupils in year 6 are divided in three classes, A, B, and C. So each class has its own column. So anything in the first column belongs in class A, anything in second column, class B, anything in third column, class C. And then we split into rows into which sport they have chosen: swimming, cricket, and gymnastics. All right, so we can see that 12 students in Class A did swimming, 4 students in Class B did cricket, 9 students in Class C did swimming. And we could start doing a whole load of things from there using all of the techniques that we have been talking about. But one thing we might want to do is look at totals, all right? Because if I add the numbers up in the Class A column, 12 plus 6 plus 10, that will give me 28. That tells me there are 28 students in Class A. All right, in Class B, there are only 15, much smaller class, and 25 in Class C. All right, and in the same way, I can find out the total number of people that swim. 12 people in A, 9 in B, 9 in C, that is 30 people swim. Doing this fast, 22 do cricket, and then 16 do gymnastics. And what's kind of interesting is, of course, if I add all these up, 30 plus 22 plus 16, total swimming, total cricket, total gymnastics, that should give me 68, which should be exactly the same as if I add up the total in the classes, because that will basically gives me the total of these 9 numbers in the middle. And, we can always do percent of A that do cricket, for example. All right, so what percentage of Class A would do cricket? 6 of them out of 28, and we're going to multiply that by 100. All right, whatever that comes out to be. Let's just get the old calculator booted up. But whatever that comes out to be, there we go. So we'll do 6 over 28 times 100, which is 21.4%, right? And we can start playing around with any amount of calculations like that. Okay? Right. But really, our goal here is to read the numbers that we want from the table. After that, we use all of our other calculations. Now, it might not be quite as simple. That previous one was a very simple, what we call a two-way table. Everything adds up. This one is a little bit harder. So we've got a bunch of software tools, and we've kept track of users who had issues, users who used it, non-users who had issues, and total non-users. All right. Now, one thing to bear in mind, let's see if we can understand this. So some people use Project Tracker Pro 18 and some people didn't. Now, what's interesting here is if I add those, right, 18 plus 42, I will get 60. If I go 28 plus 32, I will get 60. 26 plus 34, 16 plus 44, 30 plus 30. All right, so basically what happened was we had, what this tells me is there were 60 people in total, and they were given a bunch of software they could use or not use. 18 of them used Project Tracker Pro, 28 used Data Cruncher, 26 used Slide Master, and so on and so forth. All right, so those same 60 people used all of this, some did, some didn't. All right, for a variety of projects. Then within that, we can start looking at, of those users, all right, 10 had issues. So these two numbers very much go together, and these two numbers very much go together. All right. And of course, I don't have all the information here. I would assume they were given a task. 60 people were given a task about tracking a project. 42 of them didn't use the software, 18 did. And then we look at how many people within that had issues. And again, we can start comparing. So what is the percentage people using Project Tracker who had issues? Well, that would be 10 out of 18 times 100. All right, whatever that is. 10 out of 18. So 55.6%. All right. So let's just have a look there. That is 55.6%. And we could do the same thing for the 6 over 42. Going to 14.3%. And then it's up to us to make a reasonable conclusion here. All right, so it would look like actually a smaller percentage of people had issues if they were not using Project Tracker Pro for whatever the task was that they were given. So that would tell me probably that Project Tracker Pro isn't great. And in fact, you look at these numbers here, however we use this, none of this software looks particularly useful. All right, but the key thing is understanding how this data is grouped and taking a second before you start going like using a table to understand where all these numbers are. Can you figure out any patterns? Can you see any totals that are the same? Really useful little thing to do. Right, now we go on to bar charts. Now, bar charts are a real nice way to visualize frequency of various things, okay? Frequency is our maths way of saying how many. All right, but really it's just about counting. Bar charts are if I've counted a bunch of stuff in different categories. Now, those categories could be non-numerical, as in what's your favorite drink? Coke, Pepsi, Fanta, Sprite. All right, Coke, Pepsi, we probably do not need the calculator for this. All right, and we could just look it up, right? 10 people preferred Coke, right? 9 people preferred Fanta, and all we need to do is look at the height of each bar, all right? And that's it. We asked a bunch of people, how often do you work out in a week? 3 people said they worked out once, looking at this. 5 people worked out 5 times. 10 people worked out 3 times. 1 person, and looking at this, 3 people as well. Now, what we could also see is how many people did we ask? How many people did we ask? 3, 8, 18, 19. It looks like we asked 22 people total. And we can start getting information from there. All right, but we can already see that the most popular number of workouts in a week is 3. 10 people out of 22, almost half of the people work out 3 times a week, which is pretty good. All right. Here, there's a little bug here that should be separated out, but there we go. Or we could group people up, right? If we're looking at the month, there's obviously like you could work out up to 30 plus 20 times, right? People in a week work out 5 times, so say up to 20 over a course of a month. Well, that would be loads and loads of bars. So what we can do is we smooch them out. Look, we're just going to break you down into really not a lot, 0 to 3. So 3 people worked out 0 to 3 times in the month, and so on and so forth. And we can start looking that way as well. And we see it also follows a very similar pattern. In fact, it's the exact same pattern, just scaled up, which is something we would expect. Another cool thing we could do is we could draw double bar graphs. So what if we've asked, we're looking at 2 different things. So we want to look in each month, people that drink coffee, people that drink tea. All right, so monthly coffee versus tea consumption. So how often people drink coffee versus tea. I don't know if this is a single person, multiple people. I don't have that information. But what we can see is by using colors, we know that all the pink bars represent coffee consumption. So in January, we whoever it was drank coffee 10 times or whatever that represents, whereas in February, 100 times. And we could start looking, say, at the percentage increase. But let's have a look. Which month had the highest coffee consumption? That would be Feb. All right, with 100. Which drink was more popular overall in the first half of the year? So let's see. 90 there for coffee, 50 for coffee, 60 for coffee. So coffee total was 200, was 310 coffee drinks. And whereas T, we could have a look at T, that's 30, that's 60, that's 80, that was 40, that's 60. So if I add up those numbers, 90, 170 is 270. So which drink was more popular overall? Coffee. Now, how much did coffee consumption increase from February to March? Well, actually, coffee is pink. That is a decrease, but let's figure it out. New divided by old. If we want it as a percentage, new divided by old, and we're going to take away 1. So that is minus 0.1, i.e. that is a 10% decrease. Go check out our percentages video if that doesn't make if you're a bit worried about that. Now, you could be asked opinion questions here, a bit of reasoning. Why was so little coffee consumed in January? I would, top of my head, say something along the lines of New Year's resolutions. Quite a popular one, that, or I'm going to cut down on coffee. All right, but being able to take the data and not just look at the numbers, but look at what it means, where it situates, right? We're looking at January, why so little coffee, right? And then why does it shoot up into February? Well, people just did a month without caffeine and they're gasping for their coffee. Really unhealthy, but there it is. A little bit less likely is a pie chart. Now, the pie chart, we're looking at the size of the sector. So we are always representing everything as a one whole circle. And basically, what proportion of the circle you take up represents what proportion of the total you take up. So if we've got 60 children, age 4, and we're asked them what they want to be. So some said scientist, chief, adventurer, awesome teacher. Oof, bold. How many children want to be scientists? Well, if we look at scientist, that is 90 degrees, which we know from 360, 90 out of 360, that is 1/4. So 1/4 of students want to be scientists. 1/4 of 60 is 15. So 15 children want to be scientists. All right. So sometimes it's obvious what proportion. There I went full on using the angle, but we could have just done it immediately. That's 1/4. Now let's say we know the angle for adventurer here is 60 degrees. Same sort of thing, we'd go 60. What proportion of the circle is that? Well, it's 60 out of 360, which is 1/6. And then we're going to want to multiply that by the total number of kids, which was 60 kids. So 1/6 of 60 kids that is terrible. Do you know what? Everything about that puts my teeth on edge. 1/6 times 60 is 10 children. All right, and that is a pie chart. You need to be able to read data from a chart. Now, finally, this is what we call bivariate data. You are asking or measuring from the same item multiple things. So I've got some items here, 7 by the looks of it. And for each one, I've weighed it and we've asked people to give it a rating out of 10, let's say, a rating out of 10. Okay, so, and then what we can do for each item, we can plot on a graph and we want to see how the weight and the rating are linked. So I am plotting the weight down here on the horizontal axis and the rating for each item. So each item now becomes a point on a graph, right? This will become weight is horizontal, the point 10, 1. That's that one there. Point B, so that's point A, right? Point B becomes the point 35. Point C becomes the point 76, 6. Point D is 32, 4. Being careful with our scale. 40 and 7. 10 and 2. 20 and 4. All right. So that's the thing. Bivariate data, we've measured 2 or more, but for bi, it's 2. 2 bits of information for each item, person, whatever it is, and then we can plot those. They become your coordinates to plot them. So this would be my scatter graph for this. Now, what we really want to say then is we are going to look at what is called correlation. Now, correlation measures how 2 measures might be linked. Now, overall, we will call it, you've got positive, negative, and no correlation. positive correlation is when one increases, the other increases. So overall, if you look at your graph, you've got this tendency for the points to go upwards as you move to the right. Going to the right goes up. Negative is the other way around. If you go to the right, you go down. Think of it as a line on a graph. Positive gradient, negative gradient. No correlation is it's just a bit cloud and a bit messy. And we can also give it different, we can describe it a little bit further. Perfect correlation is they form a perfect straight line, as we've got down here at the bottom here. Strong is that they're not quite a perfect straight line, but they're like quite close to it. And weak, there's a trend, but not really, you can't really draw a straight line through the points. So if we go back to the weight and the rating, what would we say? Well, there is a definite clear here tendency, right, for a positive correlation. There definitely does seem to be this tendency here for the rating to go up if the item is a bit heavier. So whatever that means, people take weight as a sign of quality, whatever that means. You can then have, with a bit more context, make an inference on that. And that is how we're going to look our whistle-stop tour of different graphs where we can interpret data from.